Thank you very much, Chris, and welcome everyone to this session about analytics on AWS. As Chris said, my name is Russell Nash. I'm a solutions architect here at AWS, and I'm delighted to be spending the next little while with you talking my favourite topic, which is analytics and big data. So we talk to a lot of customers, obviously, and we talk to a lot of customers in different industries, in different organisations, different departments within those organisations about some of the insights that they're trying to get out of the data that they have. And obviously everybody's got different insights and different data sets, but what we find is that often the path to get there, the path from data through to insights, follows some similar patterns. And so that's what I want to share with you today, is some of the common patterns that we see our customers using following this kind of framework, and so that you can start to think about things in these terms, which helps to really organise your thinking around some of the different parts of a big data project, and you can look at the different tools that slot into the different areas. So this is going to be our framework for the next little while. We're going to talk about ingesting data. What are the different types of data that you might have within your organisation? Where's the best place to store that data? How do you process the different types of data that you have? And then comes the fun bit at the end, which is actually what tools do you use to analyse that data. Now before we get into that, I just wanted to just mention EC2 here. Now many of you who are familiar with AWS would know about EC2, but for those of you who are not familiar with AWS, EC2 is our most basic building block within the AWS cloud. So EC2 allows you to spin up virtual instances of either Linux, various flavors of Linux, various flavors of Windows, and that then becomes a virtual instance that you can then use as you see fit. So you can then build architectures with that, you can install on that machine whatever you like, and then manage it yourself from there. And so everything we talk about today you could actually achieve just through EC2 and putting software on it and then managing it yourself. But one of the things I want to talk about today, one of the things I want to convey to you is that on top of EC2 we also have a number of managed services, a number of higher level services, and many of them utilize EC2 underneath the covers, but what they try and do is to try and remove some of the heavy lifting away from you and let us deal with some of that. So that allows you to then spend more time and more energy focusing on the more important part of your application, which is obviously trying to get to those insights much more quickly. So let's kick off. Let's look at the first of our pieces of the framework, and let's look at the ingest side of things. And this really comes down to what type of data do you have that you're trying to look at. And we find that this typically falls into around about 3 different groups. So obviously there's database data, so every organisation we talk to has got a number of databases typically scattered throughout the organisation, and this data is highly structured. So as you know, in a database it has a particular schema, it has a particular data model that it's expecting, and so the data, once it's in there, is in a highly structured format. So we'll look at how you get that database data into somewhere where you can then start to analyse it. One of the other big buckets of data that we see customers have is log data, and this is characterised by large files typically that are full of either transactions or events that have been aggregated together and then put into a single log file. Now these might be from externally facing web servers, for example, so it might be collecting the clicks on your website, or it might even be an internally facing app server or an application that's generating some kind of metrics that you want to analyse and have a look at. So we'll look at the best way to deal with log data as well. Now often log data is referred to as semi-structured data, because while the logs themselves do have a degree of structure, often within that it can be a little messy. So sometimes you'll find that there might be one big field that's got a very long text string in it, but you actually want to break that down. You want to parse that into smaller components so that it actually makes much more sense to you from an analytics perspective. So we often see log data referred to as that kind of semi-structured type of format. And then we start talking about high velocity data as well. So this is a real area of growth for a lot of our customers who are looking at doing things in a much more of a near real-time fashion. So high velocity data is characterized by, again, its events and transactions, but instead of being put into a log file and then delivered to you in batch, they're actually fired at you pretty much as they happen. And so what you really need to do is make sure that you've got the infrastructure in place to be able to deal with potentially a very large number of devices or mobile phones or any kind of producer of events that's sending you traffic, and obviously be able to potentially deal with spikes within that as well. So let's look at storage. So where do you store this data? Where's the best place for it? Well, you'll be very surprised to know that often we find database data goes into another database. Now, there's a very good reason for that, and it's typically because the main use case here is customers who just want to be able to analyze the data that's sitting in that source database on the left-hand side there. And usually they're facing some constraints, typically around, firstly, performance. So they're finding that they're just not getting the query performance that they need, so queries are taking too long. Sometimes they have to run them overnight. They come in the next day, they've asked the wrong query, the data's not quite what they're after, they have to fire it off again, and they've already lost 24 hours of time. They're looking for that kind of interactive performance. The other thing we see is they're often constrained by, and again this is for performance reasons, they're constrained by the amount of data that they can look at. So often some of the data in those databases is maybe the last 6 months worth of data, even though they know there's 5 years worth of data somewhere in the organization, but the database can't handle that much data, so it's typically a rolling 6 months is all they have access to. And along those lines, the other thing they sometimes say is we actually don't get access to the low-level data. We don't get access to the individual transactions or events. By the time we get to query it, it's already been summarized and rolled up, and again it's to help that database deal with the SQL queries. So that's why typically customers are looking for an analytics database to solve these issues, to get that processing off their source database and into somewhere where they can then analyze it. Now there's a couple of the managed services we have that customers look at for this. One is Amazon RDS and the other is Amazon Redshift. So looking at first at RDS, so RDS is what you'd think of as your traditional relational database. And you have a choice of engines that you can see here. So you can see there's a couple of commercial engines. There's Microsoft SQL Server and Oracle, and then you have some of the open source databases such as MySQL, PostgreSQL, MariaDB, and then Amazon Aurora, which is an Amazon developed database that's MySQL compatible. Now, as I said, you could install these databases on EC2 yourself. The advantage you get with RDS is that it's very low maintenance. So with RDS, we'll make sure that we procure the hardware underneath for you, we'll provision that hardware, we'll then install the database, we'll back it up for you, we'll patch it, etc. So it just takes that concern away from you. Now looking at Redshift, so Redshift again, it's a managed database. The difference here is that Amazon Redshift is an MPP SQL database. So MPP stands for Massively Parallel Processing. And really what that means is that it scales horizontally, so you add more nodes to the cluster if you need more space or more performance. And it's really optimized for analytics. So it's really designed specifically for those queries where you're asking questions of the database. You're asking it to scan through lots of data and give you a result. It's also very scalable. So because of its horizontal scaling nature, you can actually push Redshift to very large volumes indeed. And we do have some customers who have scaled all the way into the petabyte range with data in Redshift. So it is able to cope with very large data volumes. So I wanted to put these two side by side because often customers ask, what is the key difference between an RDS and a Redshift? There seems to be some overlap in the functionality that they have. So I wanted to put them side by side. First of all, let's talk about what type of database they are. And this is an important fact that they're both SQL relational. So you drive them with ANSI standard SQL. They're fully relational, so you create tables, you create a data model, you create relationships between the tables. You do that in both of those databases. But as I said, the scaling factor is different. The way that they scale is very different. So with databases like RDS, when you need to scale it, when you need it to be faster or more performant, you typically scale it vertically. So you'll actually increase the performance of the machine that it's running on. But obviously that only takes you so far. Databases like Redshift, they scale horizontally. So you're adding more nodes. Those nodes are in what we call a shared nothing architecture, so they don't actually share network and CPU and memory with any other node, and this then reduces contention and allows you to scale up to very large volumes. So you can see here why the volumes, RDS great for low to medium volumes, Redshift really takes it from medium to high and through to very high. So what does that leave us with in terms of workload? So RDS great for a mixed workload. So you'll see it used for a lot with transactional type of workloads, where you're inserting a row, deleting a row at a time, that kind of thing. It can do analytics as well, but typically on smaller data sets. Once you get into a certain range, you really want to start using Redshift for analytics. Now, I can hear you shouting at the screen. So what is that? What is the cutoff? When should I move between RDS and Redshift? So there's no real hard and fast rule, but typically I say to customers, once you get into the 100, 200 gigabyte range and you're doing some analytical type queries, that's where you want to start thinking about potentially a move to Redshift, or that's where you might start to see the value in terms of performance with Redshift. A great example of this is SoundCloud. So SoundCloud, a lot of you might be familiar with. It's a platform that allows bands and solo artists and podcasters to upload audio content, and then those links are then shared on social media and websites and blogs and apps, etc. And then users can download that and then listen to them. It operates at a massive scale, so I think about 12 hours of audio get uploaded to SoundCloud every minute. And then along with that, there's obviously very high traffic in terms of downloads, etc. So SoundCloud generate billions of events every day, which they then want to analyze, because this is obviously key to user behavior on their platform, and they use Redshift for that. It's a perfect use case for Redshift, where they can just upload those events into Redshift and then do that analysis as they need to. So how do you get data into RDS or into Redshift if you already have a database perhaps sitting on premise? Well, it's actually no different to how you've been doing it for many, many years, and is to use ETL. So ETL stands for extract, transform and load. So extract from source, potentially transform the data in some way and then load it into the target. And you can see here there's a number of different options to allow you to do that. So we have many ETL partners. A lot of these tools are very mature, they've been around for a long time, and their expertise is in getting data out of that source system and then pushing it into the target database. We also have the AWS database migration service, which you can also look at in that space as well. Now, you may want to do this as a one-off. You may actually want to move that source database and then turn it off, or what's also quite common is you're using that source database as a transactional database. It's actually being used as the back end for some kind of application, and you want to keep it running, and you actually want to propagate those changes on a continual basis into your target analytics database. And the ETL tools will definitely allow you to do that. So that's typically where database data goes. What we find with log data is that can go into a number of places. Now, I've shown it going into search engines and storage here. It can also go into Redshift as well. We actually have quite a few customers who use Redshift for log data as well. So as we go through and you look at this framework, there's no hard and fast rules here. These are just kind of some of the patterns we see, but you can certainly mix and match as you see fit. So let's have a chat about search. So often people don't think about analytics when they think about search. They think about more a kind of a single query where they're actually just searching for a single word or a phrase, etc. But what's happened over the years is that Elasticsearch in particular, which is an open source search engine, started off as a full-text search engine, but people found it to be so useful and so scalable because of its distributed nature that they started using it for analytics as well. And what we found was we had a lot of customers who were running Elasticsearch on EC2, and they said to us, hey, AWS, we love Elasticsearch, we don't really enjoy managing it, can you please do that for us? So that's what we did. So Amazon Elasticsearch is a managed service. It's a managed version of the Elasticsearch open source project. So as I said, it's both full-text search engine and analytics, very scalable, and it's integrated as well. So there's a couple of other open source tools that plug into Elasticsearch. One is Logstash, which helps you to move data into Elasticsearch, and the other is Kibana, which gives you the visualization on top of Elasticsearch. This is often referred to as the ELK stack, so E for Elasticsearch, L for Logstash, and K for Kibana. This is what Kibana looks like. Many of you may be familiar with the Kibana front end, and so you can use this to develop your own dashboards and your own graphs, your own analytics. Fantastic for real-time dashboards to give you that real understanding of what's happening in your environment. The other place that we see logs going into is into more generic storage, and there's a couple of places that this tends to happen. One is Amazon S3, and the other is into HDFS, so HDFS being Hadoop's distributed file system. So let's have a little look at S3 first. So S3 is another one of our basic building blocks in the AWS cloud, and this is our object storage service. So object storage, you can load up pretty much anything you like, media files, log files, you name it. And the great thing about it is that it is low cost, but it's also extremely durable. So every object that you send up to S3 will actually write that to multiple locations, multiple physically separate locations within a region. And this is how you get this extremely high level of durability that you see there, 11 nines of durability, which is extremely important to a lot of our customers. And so what you'll see is that even though S3 itself is just storage, it doesn't have any processing capability, people use it to store their logs and their files to then process with one of the other engines that we've got. And I'll show you how we do that. Now first let's have a quick chat about HDFS. So HDFS, as I said, is Hadoop's distributed file system. And basically what it does is it acts as a layer of abstraction across the machines in the cluster. So you spin up a Hadoop cluster. In that cluster obviously there are machines that have got disk in them, and HDFS sits across those disks and abstracts that from the Hadoop processing layer plus all the other fantastic tools that you get to plug in at the top. So HDFS will manage the distributed nature of the objects, it will replicate them as many times as you tell it to, it knows where they all live, etc., etc. And so sometimes we see customers, they will spin up a cluster, they will keep that running, and then they will load data directly into HDFS and then do their processing from there. Now, so obviously you can do that yourself. You can spin up those machines. They could be EC2 machines. You can install Hadoop yourself. You can manage the cluster. You can install the applications on the top. There is another option though, which is a managed version of that, which is Amazon EMR. And this is our managed Hadoop service, which again takes away the heavy lifting out of spinning up and maintaining that Hadoop cluster. So basically you talk to the EMR console or through the CLI, the SDK, you tell us how big you want the cluster to be, what applications you want installed. We will then go and provision those machines, make sure they're all talking to each other, and then hand you the cluster and off you go. Which is fantastic because managing Hadoop clusters is not particularly easy, and so Amazon EMR is designed to take that heavy lifting off your plate again and onto ours. Now EMR comes with one other really important component which leads to a whole raft of goodies which I'll talk about in a sec, and that is EMRFS, so EMR's file system. And what this allows you to do is it allows you to talk to S3 from within Hadoop. So this then allows you to inherit all the goodness that we talked about with S3, its scalability, the low cost, the very high durability, and use it as your storage layer for your Hadoop cluster. Now what this means now is that you are breaking the connection between compute and storage. And that's really powerful, because if you think about, if you've got a cluster where you're just using HDFS, your compute layer and your storage layer are bound together on those machines. So for example, if you want more disk in your cluster, you have to add more machines, which brings with it more compute. And you have to pay for that, obviously, even though you don't necessarily need it. You might just want the disk space. You might not need the extra compute. But by breaking that connection, you're then able to scale each layer independently. So if you need more data, you just load up more data into S3. You don't necessarily need to then pay for a bigger cluster. And that leads to other benefits too. So you can actually potentially shut the cluster down when you finish with your processing, stop paying for it, the data is safe in S3. When you're ready, spin the cluster up again and then access the data in S3 again. So we see a lot of customers use that kind of model where S3 is their source of truth for data, and they just spin clusters up and down as they see fit. So another added benefit of doing something like that is being able to take advantage of the different instance types that we have in the EC2 family. So as a lot of you would know, we have different families of instance types that have different configurations and different ratios of CPU to memory to disk to network, etc. And if you look at a lot of the big data types of workloads that we see, they typically really like certain configurations. So a batch process is not very fussy. It's quite happy with a general purpose machine, whereas machine learning tends to be quite CPU intensive and really loves the C3 and the C4 family of machines. When you start looking at some of the more interactive and the more query-based types of tools like Spark and Presto, etc., they love memory. So they love clusters with lots of memory. So having this ability to have your data in S3 and then spin up a dedicated cluster for a very specific purpose is extremely powerful, because it allows you to not only map what your workload is to that cluster, but also spin up multiple clusters that don't interfere with one another. So they're accessing the same data set potentially, but they're actually not treading on each other's toes in terms of computation. So again, that's a very common pattern that we see with customers, is to spin up different machines for different purposes, or different clusters for different purposes. Now, one of the other things that you then get to take advantage of is this fantastic relationship in the cloud between cost and time. So if you look at the way that you pay for compute within the AWS cloud, you're essentially paying for the number of CPUs and the length of time that you use them for. So in this example here, let's say we have a job and we have one CPU running that job, and let's say it takes 10 hours for that to run. You will then pay essentially for that red rectangle. You'll pay one CPU for 10 hours. Now, if that process is one that you can then spread across multiple CPUs, as we see in most big data workloads, you can then do this. You can throw more CPU at it and get it done in less time. So let's say you throw 10 CPUs at it and it finishes in an hour. Now, you're still paying for exactly the same amount, because you're still paying for that red rectangle, but your job's finished in a tenth of the time. And this is the real attraction for people into the cloud for big data computing, is the ability to throw a lot of resource at their process for a short amount of time and get it finished. And that's of tremendous benefit to the businesses that they support, because it allows them to get an answer in 1 hour instead of 10 hours, or an answer in a minute instead of 60 minutes, while not actually paying any more for that particular process. Now, as you know, at AWS we love to push things even further to try and save customers money. So we have the concept within the EC2 fleet of a spot market. Now a spot market is where we have unused capacity. We will then make that available for customers to bid on. So every different instance type in each availability zone is its own separate spot market. And the way this works is that there's a volatile price, so a spot price that moves up and down depending on supply and demand. If you then make a bid for a particular instance type and your bid price is above the current spot price, then you then get to use that instance for that particular at that price. Now the caveat being that if the spot price goes up and it goes above your bid, then we may take that instance away from you. So it really works for processes that can tolerate the loss of a node. So let me give you an example. So let's say we're looking at the M3 2 extra large, one of the general purpose machines, and in Sydney it's got an on-demand price of 75 cents per hour. Now as I said, the spot price does fluctuate, but it often fluctuates around the 8 cents per hour mark. So you can see it's almost a tenth of the on-demand price. Now, as I said, obviously you need to have a process that can tolerate the loss of this node if we take it back. But what we've done with EMR, with the managed Hadoop process, is we've actually embedded the ability to use certain types of nodes that don't have disk attached, that are great for spot, because then if the cluster's running along happily and that task node gets taken away, the cluster will continue to run because it's got other nodes in there, and you don't lose any data because the task node didn't have any data attached to it. It was just processing. So that's a fantastic way to spin up even larger clusters than you would normally, use the spot market as much as possible, and again just get that processing finished quickly. A great example of a customer using EMR is Upserve. So Upserve provide a cloud-based restaurant management system for their customers. So they will collect from the restaurant, they'll collect reservation information, they'll collect credit card payments, menu trends, then from the web they'll pick up online reviews about that restaurant, etc. And so you can imagine they've got a huge amount of data coming in from all the restaurants that they support, which they then bring it in, they then sort through it, and then they produce analytics, which they then provide back to the restaurant for them to then obviously look at and plan accordingly. And they use EMR as a core piece to actually do a lot of that, that processing when that data lands. One of the other interesting things they're doing is to actually start to do predictive analytics as well now. So based on the data that they have about your restaurant and other restaurants, they'll actually predict for each restaurant how busy they think it's going to be on a particular night. And you can imagine for a restaurant, that's fantastic because that really allows them to plan in terms of staffing and supplies, etc., etc. So a great example of really using data to great effect. Right, so looking now at high velocity data, as I said, high velocity data is an interesting beast because it's got, it raises some interesting challenges because you've got potentially a lot of volume and that volume can be quite spiky, but it also provides fantastic opportunities as well because you're getting access to that data in near real time. And so the possibilities are endless where instead of getting a batch that might be an hour old or 24 hours old, you're getting your hands on that data a couple of seconds after it's been produced, and that's incredible. So how do you deal with that? So there's a couple of options. You can use a stream processor, or you can look at NoSQL to do that for you as well to help capture. So let's look at the stream processor that we have. The managed service that we have is called Amazon Kinesis. And one of the first things that's important about any capture mechanism for these types of messages is that, again, it needs to be durable. You can't drop messages. So you'll see that Kinesis sits across 3 availability zones, similar to S3, and again, that gives you that really high durability. So you create a stream within Kinesis, and then your data sources push data into the stream. Now then what happens at the back end is you then use a variety of mechanisms, which I won't go into here, but you can choose a number of mechanisms that potentially might be an app running on EC2, or it might be a Lambda function, to then pull the data off the stream and do different things with it. Now let me give you an example of some of the stuff you might do. So let's say you want to do clickstream analytics and you want to do it in near real time as opposed to batch. So the data coming in is every single time someone clicks on a link on your site that's sending an event through. So the first thing you might want to do is simply to keep a log. You want to have an audit log of every single event that happened, unadulterated, unchanged, untransformed. You just want the raw stuff, and you want to keep that so that if you ever need to go back, you can do that. So S3 is a great place to do that, obviously. But then you also want to have a real-time component as well. You want to have one of those Kibana dashboards that's showing you in real time how many people are on the website, what kind of latency are we seeing from our web servers, are we seeing any 404 messages, all of that kind of thing. That stuff is key to that kind of near real-time view. Then you might want to potentially push that data into an Hadoop cluster, into EMR for example, maybe because you want to do some recommendations. Based on what the customer's looking at, you might decide, okay, we want to recommend a particular article to them or a particular product, so to be able to react in near real time. And then for a longer term view, you also want to push the data into Redshift so that you can then start to do some interesting analysis about, when did this person first come to the website? Maybe they came to your website 3 months ago and then they've come back and purchased. What kind of path through the website did they take? What changes can we make? So Kinesis is fantastic for that because it allows you to capture those messages durably and then allows you to then take them off the stream at the end and do different things with them. So each of those different applications at the back end, those different targets, they're all getting the full stream, but they're not interfering with one another because they checkpoint at different rates within the stream, and that's the beauty of a processor like Kinesis. So moving now to NoSQL. So the managed service that we have in the NoSQL space is Amazon DynamoDB. And I just wanted to say a couple of words about NoSQL. I love NoSQL. I love the fact that they bake into their name what they've taken a stand against. We've taken a stand against SQL. We're NoSQL. So depending on who you talk to, it's either NoSQL or not only SQL. But either way, they're taking a fairly strong stance. And really it was born out of a frustration with traditional relational databases and their inability to scale when people really needed them to, when they had them behind a website. So people were looking to, in the old days, go beyond the static website, put in a database, allow customers to upload content, also be able to serve content, and they found that as those websites grew in popularity, the relational databases couldn't keep up. So as is typical in the world of IT, it's always a trade-off. So what they found was that they could trade off data complexity for scalability. So if you look at where the relational database sits, it gives you some fantastic data structures, some real complexity, but at the expense of extreme scalability. So the NoSQL people said, well, actually, let's drop some of those features. We actually don't need those kind of rich structures necessarily. We don't need things like joins. We just want scalability. So that was the trade-off. So you can see now NoSQL at that top end giving you that extreme scalability. Now the reason that oval is so long is because there are several different types of NoSQL database. So there's the simplest one, which is the key value store, and this is where you just get a primary key and a value. Very, very simple structure, but gives you extreme scalability. Then people said, oh, we want a bit more structure, so that's where document NoSQL databases were born. So documents here, we're talking about JSON documents, so potentially nested structures where you can actually have a little bit more complexity in your data. And then graph databases as well. So graph databases, fantastic for analyzing relationships between entities. Great for any kind of network analysis, be it a social network or otherwise. So that was just a bit of background on NoSQL. Dynamo is a NoSQL database. It's both a key value store, but it also has document capabilities as well, so you can put your JSON payloads in there if you like. And what you get, as you do with most NoSQL databases, is extremely low latency for reads and writes. And when we talk about low latency, we're talking about a consistent response, and this is what customers really need when they're using, because typically people will use Dynamo in a front-facing capacity, so their customers will be hitting that database, and so they want to make sure that the latency is low and the latency is consistent. And so you can see here that even as the number of requests fluctuates, that response time should be pretty standard, pretty consistent. A great example of a customer who uses not just Dynamo but also uses Kinesis and also Redshift is a company called Hello, and they have a device that they call Sense. That's the ball sitting there, and it sits next to your bed, just on your bedside table, and there's also a little clip-on that clips onto your pillow as well. And it's designed to collect a lot of data about the environment that you're sleeping in and also your own patterns to then help you to sleep better. So it'll pick up things like the amount of light, the amount of noise, how much particles there are in the air, etc. All of that data comes through Kinesis. A lot of that ends up in Redshift to be analysed, and then they place the results into Dynamo for that front-end application. So the application that you see there on the phone is going to be hitting Dynamo. So a great example of using each of those services for exactly what they're designed for. So you're using Kinesis for the streaming events, Redshift for the heavy-duty analytics, and then Dynamo to serve that data very quickly to consumers when they look it up. So that's ingest and store. Let's have a little look now at the next stage, which is process. Now, obviously, you can see that some of those technologies we've talked about have processing in them as well, but there's also other technologies too that can help you here to either do an interactive type of approach, so kind of where you have a human who's sitting there trying to query the data, but obviously batch. You have a lot of batch processes as well, and then you also potentially want to process the streaming data that's coming off your stream processor. Now, Redshift we definitely see sitting in that interactive area there because it is designed to give a human that interactive response that they're after, where they'll ask a query and then get a response and then potentially ask another query. But there's a couple of other options as well. So we also see things like Presto and Impala here as well. Now, these are open source MPP engines, massively parallel processing engines like Redshift. The difference is that Redshift has its own dedicated database with dedicated storage, whereas Impala and Presto actually sit across a Hadoop cluster, and then they'll access data either in HDFS or in S3. And you can see there that Hadoop and EMR are just slowly going further down the page because they're taking up more and more of the different processing workloads that big data is producing. When you get into batch, you can see Spark there straddling both interactive and batch, which can do both. We'll talk about Spark in a sec. And then you've got some of the workhorses of big data such as Hive and Pig, who've been around for a long time, usually very much in that batch kind of space. Let's have a quick chat about Spark, because Spark gets a lot of press in the big data world, and rightly so. It's really started to become the next generation of processing engine. Now, a lot of people talk about Spark versus Hadoop. It's not technically correct. It's really Spark versus MapReduce. So MapReduce was the original processing engine underneath Hadoop, and that's what Spark's replacing. But Spark is often used in a Hadoop context as well, even though you can run it standalone too. Why do people love it? Well, firstly, because it's pretty fast compared to MapReduce. So it makes much better use of memory, and it's got some other processing tricks up its sleeve as well that make it orders of magnitude faster than the MapReduce framework. It's also pretty flexible, so it's much easier to use than MapReduce. It's also pretty rich, so you'll see that you get a lot out of the box with Spark. So there's the Spark core, but there's also Spark SQL, so you can actually run SQL-like queries with Spark. There's Spark Streaming, which can help you to ingest streaming data. There's also Spark ML, which is for machine learning. So it's really got a lot of stuff in there out of the box that makes it really attractive. And then the last thing is it's got incredible industry support. So it's really reached the point now where every single big data player has put their support behind it, and that makes it very difficult to be overtaken by another technology. So I think we'll see Spark here for a while yet. So let's move down into streaming, and to my point, you can see Spark Streaming pops up there. So one quite common pattern is to use Kinesis as a capture mechanism for your events and your transactions, and then actually have Spark Streaming reach into Kinesis and pull those events out, and then actually process them within the Spark cluster or the Hadoop cluster. Alternatively, you can use Kinesis consumers, so that could be a consumer running on an EC2 machine that can be doing a variety of tasks. And then also Lambda as well. So Lambda being an event-driven serverless approach where you just send us the code. You don't actually have to manage the servers. We'll basically just run your code in response to events. That's quite a popular way, again, of managing the events coming out of Kinesis. Now I wanted to just compare a couple of these technologies in a couple of different ways, because obviously there are lots of technologies out there, and I wanted to look at this really from a query perspective. So less of a kind of a batch process and more of a query perspective. If you had data that you were querying, what are the different facets that you'd be looking at along these different technologies? And what I'm doing here, I'm not trying to say that one is better than the other. I'm really pointing out what their different sweet spots are and what they're really designed for. If you look at the data structures that they support, Spark and Presto can deal with semi-structured data. The data that goes into Redshift has to be fully structured because it's a database with a predefined schema. Elasticsearch can deal with pretty messy data as well, so you can put semi-structured data too. In terms of languages, Spark's got multiple language support. You can write in Scala, you can write in Python or Java. Presto and Redshift are SQL engines, so you're going to drive them through SQL. So you can see that immediately if you're looking for a SQL type engine, even though Spark does have a SQL engine as well actually, I should say, but Presto, that's its primary interface, is SQL, similarly with Redshift. And then Elasticsearch, its interface is more about either through Kibana or through kind of the type of language you'd expect from a full-text search engine. The data stores that it supports, so Spark can read from S3, it can also read from HDFS, as can Presto. Redshift and Elasticsearch have got local storage, so you'd actually, with those two, you actually load data into them from somewhere else. And so you can see here, if you're living in a completely Hadoop-centric world and all your data's in S3 or HDFS, and you wanted to give it SQL access, then maybe Presto is the right choice. Potentially, if you have got other databases and you're not really in the Hadoop world, then potentially Redshift is a better choice. And then if you look at performance, now performance obviously varies depending on the workload and what you're trying to do, but as a general rule, if you're just comparing the query speeds of some of these engines, Spark's typically, because it's more general purpose, is probably the slower of the four. Presto is designed to be pretty quick. Redshift is faster again because it's got that direct attached disk and it's a dedicated database. And then Elasticsearch is also pretty fast as well for the types of processing that it does. So what are the use cases for these four? So Spark's a general purpose processing engine, as I said. So it does have a SQL interface, it does do machine learning, you can run R on it as well, so it's really a general purpose engine. So it's a real kind of spanner that you can use in all sorts of different ways. Presto is specifically for running SQL on data that's either in S3 or HDFS. Redshift is a fully featured SQL database with all the bells and whistles you'd expect. And Elasticsearch is a full text search engine that also has that visualization component as well. So let's finish off in terms of analyze. You can analyze the data in these engines in a number of ways. So there's obviously the business intelligence tools that have been around for a very long time. Plenty of fantastic partners in that space. There's also Amazon QuickSight in there too. Kibana, as I said, is the front end for Elasticsearch. For statistical type of analysis, you can obviously use R, that's very popular. And then on the machine learning front, you've got the Amazon Machine Learning Service plus a number of other open source options as well. One of the ones getting traction at the moment is the machine learning libraries within Spark as well. So that's the end-to-end framework that I wanted to share with you. And as I said at the beginning, it's really just a framework that we see a lot of customers using. Now, obviously, there's no hard and fast rules about what you use with what. You can mix and match. Data can go from pretty much anywhere to anywhere, but that's really just to give you something to kind of look at the tools that are out there and kind of see where they fit in the whole big data pipeline. Now, what I'd love to do now is open it up for questions. Now, while you're thinking about some questions to ask, I wanted to just pop this up as well. We've started a podcast in Australia that's aimed at an APAC-wide audience called Tech Chat. It's really designed to be a different medium for you to consume technical knowledge about AWS. We talk about best practices, we talk about service updates, new services, we'll have guests on, etc. So, so follow that black bit.ly link, and that'll give you all the details, and you can see the episodes that we've got up there already, or you can just subscribe via iTunes or SoundCloud as well.